This is the second thermodynamics video, and we'll start with the calorimeters. You should have maybe done this experiment before we went on break. If not, I think you're going to have a virtual calorimeter experiment. In any event, this is the background material for it. So in this situation, you're interested in measuring the heat of a chemical reaction. Doesn't have to be a chemical reaction. It could be, something dissolves in something else and there's some heat given off. So the heat of solution formation, perhaps. I think you work with hot water and cold water in the lab. So you're looking at exchange of energy between the hot and the cold molecules. But I'm going to talk about a chemical reaction that takes place in the coffee cup calorimeter in a few minutes. So it'll be an acid plus a base forms salt plus water, and then there'll be heat given off. And you can measure the heat of the reaction if you can you can calculate the heat of the reaction if you can measure the temperature associated with the reaction that's taking place inside these coffee cups. So notice there's two here. You would start with one with the acid solution, the other one with the base. You pour one into the other, and then you kind of nest the two cups to allow for good insulation. It's never good with the coffee cups anyway, but we try. In our lab, I think we're still we're using like a styrofoam, I think, lid, which doesn't really serve the purpose too well. The heat still does escape, but we ignore all that stuff and just get the general idea. So here's a stirrer. So the solutions are stirring, the reaction takes place, the heat's given off, and supposedly the heat does not escape through the walls of the cup. Instead, it heats up the solution, and then the solution temperature increases. All right, and then type of calorimeter. This one's called the bomb calorimeter. We work with these in the physical chemistry labs, Chem 352, so it's upper division. And here, this part is called the bomb, and it is a stainless steel container. You can screw this cap on, and it's very, very tight. So this is a closed system. When we measure heat, it's going to be delta E. With the coffee cup, it's going to be delta H. Not that we care about that, but I explained that in the last video. We don't care about the difference between delta H and delta E. Anyway, it's a closed system, and you can't see it here, but usually there's another port right here where you can add oxygen at high pressure. You might get like 25 atmospheres of oxygen in here. You just, from a separate tank, you pressurize it. All right, the sample is usually solid, doesn't have to be though, and it is a combustion reaction that takes place. So you have an ignition wire, so here's a metal electrode, and then some wires that come down inside the bomb. And then finally, you don't see it, but there's a piece of nichrome wire that's connected to this whole thing, and that nichrome wire is sitting right above the sample. Nichrome is a material that ignites when electrical current goes through it, so it's perfect for this job. So in the presence of oxygen, the nichrome has a flame, which then is going to ignite the sample. So the sample's going to burn, and we have the reaction of usually it's an organic molecule, doesn't have to be, but something with carbon, hydrogen, those are commas, carbon, hydrogen, and oxygen, some unknown. And you react it with O2 to form CO2 plus water. And it's all in the gas phase. On the right-hand side, the CO2 is gas phase, water evolves in the gas phase, and then when it comes down to room temperature, it ends up being 25 degrees C or 298 Kelvin. All right, but anyway, there's heat as well. And the heat transfers from the bomb to the water. So this is sitting in a great big water bath. And this stirrer actually goes down further, and it's spinning. So it's stirring the water, dissipating the heat. And you're looking at the temperature change, which is basically due to the heat of the reaction that heats everything up. So in the case of the calorimeter, we have a different equation. We have the entire calorimeter that heats up. We have, in the case of the coffee cup, it is just the solution that heats up. But in this case, the bomb heats up, the gases inside the bomb heat up, the water heats up, the inner part of the chamber heats up, the thermometer heats up, the stirrer heats up, everything. And so we use a constant. We have to figure it out with a known sample here. Figure out how much heat is needed to raise the temperature of the entire thing by 1 degree C. And that's given the symbol W for the calorimeter constant. And it's best seen if you look at these two calculations, two examples. There is another, the next one is, the next slide is for the coffee cup calorimeter. All right, so we have two coffee cups. One of them has 33 milliliters of 0.1 molar, 1.2 molar HCl. The other coffee cup has 42 milliliters of a solution of sodium hydroxide. It just says excess here, so that is telling you that the HCl is the limiting reactant. You know, if I said 42 milliliters of 0.2 molar, then you'd have a limiting reactant problem. You'd have to calculate moles of each and figure out the smaller one based on the coefficients and then use that in the end. But not the way this one's written. We already know that the HCl is the limiting reactant. So the solution temperature rises from 25 to 31.8 degrees C, and we can calculate the enthalpy change. That's delta H, which is Q, right? Per mole. See how it says per mole of HCl consumed? That means per mole of limiting reactant. And we're going to make some assumptions that the heat capacity and the density of the final solution are the same as those of water. So the heat capacity of water is 4.184 joules per gram degree C. And the density of water is 1.0 gram per milliliter. So we're saying that the solution is dilute enough that the heat capacity of the solution is the same as that of water, and the density of the solution is the same as that of water. So we're going to use those numbers right there. All right, so then we need to think about, this is kind of hard to visualize. It's not a hard calculation, but kind of getting a picture of it makes a big difference as far as seeing what goes where. Okay, so here's one coffee cup. Here's the other coffee cup. The first one is 33 milliliters of 1.20 molar HCl. The second one is 42 milliliters of NaOH, and it doesn't matter what the concentration is because there's more than you need for the reaction. All right, the next step here is to pour the sodium hydroxide solution into the cup that has the HCl. So in the end then you're going to have 1 cup kind of nested, yeah, right. After you pour it in, then you put that cup underneath, so you have a double cup now. But this is the mixture here, and the reaction takes place. You cap it, you put your thermometer in there, basically, you stir it up and so on, and then you measure the delta T, the temperature change. Okay, which in this case is 31.8 minus 25.0. So that's going to be, if I got that right, 6.8 degrees C is delta T. All right, now the solution has what volume? So here the volume is 33 plus 42, so the volume is 75 milliliters total. The two solutions are mixed together now. So we need that information with the density to get the mass of the solution. So let's continue along here. If you take 75 milliliters, multiply that times 1.0 gram per milliliter, the density of water, then you're going to have 75, doesn't matter what the sig figs there, grams of water. It does, if in the real life it does matter, but for what we're doing it doesn't matter. Let's just get the idea. All right, so you have mass, and you've got delta T, and we're going to use C of the specific heat of water as our heat capacity for the system. Now, students tend to mix everything up. It's not a hard calculation. So we can say Q is equal to MC delta T. We're looking at how the solution heats up. We're not looking at the moles that heat up. We're looking at the solution that heats up. So one of the key problems is the mass. You know, when you look at this equation, M, what is mass? This is the mass right here. It's the mass of the solution. So 75 grams. I'm going to use the specific heat capacity, 4.184 joules per gram per degree C. And then delta T here is 6.8 degrees C. Q is equal to, oh, and also you want to put a negative sign in there. Negative means heat's given off. That's just a convention. You can just stick that in there. So this is negative 2133 joules. All right, now if you go back and read the problem again, give the enthalpy change. Give the enthalpy change per mole of HCl consumed. So what we've got here is the enthalpy change, because this is delta H, right? But it's not per mole consumed, it's per 75 grams consumed. And if you wanted to put that in your lab report, nobody cares how many grams you were using and how much heat you got. We want to know how much heat there is if you had a mole of substance. So that's what this is all about here. Give the enthalpy change of HCl consumed per mole as opposed to per 75 grams. So you're fine with what we've done so far, but then we want to, we want to calculate the number of moles of HCl. All right, so to get the moles of HCl, we're going to use the fact that we started with 33 milliliters of 1.2 molar solution. So we know that molarity times volume is moles. So we're going to say 1.20 molar times 0.033 liters. And that is going to be equal to 0.0396 moles of HCl. Now you don't take the 75 grams of solution and try and use molar mass for HCl to get moles of HCl. That is absolutely incorrect. You want to use molarity times volume is moles. So molarity times volume equals moles. All right, now we got our moles, and then the next part here is to take the heat and divide by the number of moles. So earlier I was saying that delta H and Q are the same thing. Well, they are, as long as it's a mole of substance. You want to look at the difference here. Delta H is going to be Q, whatever your heat is, divided by whatever your moles are. Okay, so that's not 100% what I said before. In fact, I didn't say it at all. So this is some new information. Delta H we calculated to be negative 2133 joules divided by the number of moles, 0.0396 moles. And we're going to get negative 54,000 joules, which is equal to negative 54 kilojoules. Okay. Well, that's a significant amount of heat associated with this reaction. If you had, if you carried that reaction out in a beaker and you were holding it in your hand, you'd feel the heat associated with that acid-base reaction. Okay, so then before we look at the bomb calorimeter calculation, in summary, we have delta H is Q divided by N, and delta H is equal to MC delta T divided by N. And this is probably the way you want to think about this, as long as you're being asked to do it per mole. So you have the mass of the solution, specific heat capacity of water, change in temperature that's measured, and this is the moles of the limiting reactant. So I don't know how else to tell you. It's very easy to get this stuff mixed up. Here's the equation. M is the mass of the solution, 75 milliliters, right? 75 grams. This is the heat capacity of water. As long as it's dilute and it says that you can use water. Delta T is the heat for the reaction, and this is going to be moles of the limiting reactant that we got from molarity times volume is moles. All right, mass and moles get mixed up by students, and people start putting in moles on the top and using volume to count. It gets really crazy. It's not a difficult calculation as long as you've got it all sorted out and you know what to put where. Okay, so then next calculation will be for the bomb calorimeter, and this time you've got a solid sample. It's graphite. Graphite is just carbon. It's not, doesn't contain the hydrogen and the oxygen, so it's a little bit simpler. When it's oxidized or combusted in the bomb calorimeter, you get CO2, not the CO2 in water that I discussed earlier for most samples. So anyway, you got some graphite, that's just carbon, and you get the mass of it. Put it in the bomb, you add the excess oxygen, and this is saying that after the reaction takes place and then comes back to room temperature, the temperature is going to be 25 degrees C. So the temperature does go up, no doubt about that. And also, as a result of the combustion, the temperature rises up to 25.898. So the delta T is actually the difference between these two, even though in the end the temperature comes back to 25 degrees. All right, then the heat capacity of the calorimeter and its contents. So that's what I was discussing before. This is the value of the calorimeter constant that has the symbol W. And then what is the heat of the reaction per mole of carbon combusted. Okay, now the equation we want is Q is W delta T, and we are going to put a negative sign there. Heat's given off in this one as well. W is the calorimeter constant, and then delta T we know, and Q we're going to calculate there. Okay, so in this case, this is equal to 20.7 kilojoules per degree C. Okay, easy enough. And in the end, notice it says per mole of carbon, so we're going to do that again. We'll see that delta H will be equal to Q divided by N, just like in the last example. Okay, let's put it all together. We have Q, negative because heat's given off. W is 20.7 kilojoules per degree C, and that is multiplied times delta T, the difference in the temperatures, which is 0.898. So that ends up being negative 18.4 kilojoules. Next, we want to, that's Q. Next, we want to recognize that this is 18.4 kilojoules for the read the problem again, for the 0.562 grams. That's not per mole, If you want to report this to other scientists, you would want to convert that into moles. You want to have how many joules or kilojoules per mole. Okay, so then we come back over here. So this is 4.562 grams. Next, we want to use delta H is Q divided by N. We need to calculate the moles. So the moles of what? In this case, it's going to be the moles of graphite. And so we have moles of carbon or moles of graphite will be equal to the 0.562. Let's see. Yep. 0.562 grams. This is carbon, so it's going to be 12.01 grams of carbon per mole from the periodic table. The moles of carbon are 0.0467. Graphite or carbon. And put it all together now. Delta H is negative 18.4 kilojoules divided by 0.0467 moles, and then delta H equals negative, and let's convert to joules, so 10 to the third joules per kilojoule, and this ends up being negative 3.93 times 10 squared. No, that's kilojoules, sorry. Let's see, it'd be 10 to the fifth, I guess. (10 to the fifth joules per mole, which of course is negative 3.93 times 10 squared kilojoules per mole. So either way is fine. Probably kilojoules, I guess. All right. So that's the calorimeters. It's hard to keep it all straight. Take some good notes on this and practice it several times to help you see things clearly on this. All right, the next topic is enthalpy change, and the fact that enthalpy is characterized as an extensive property. And extensive, not something we talk about every day, but it means that it depends on the quantity of the material used. And for the combustion of methane, to get methane plus oxygen forms CO2 and water, then delta H for this, notice it's per mole here, it's negative 890. So heat's given off during the combustion of methane. And notice this is per mole of methane consumed. We also could say per 2 moles of oxygen consumed, or per mole of CO2 formed, or per 2 moles of water formed. But I happen to write it that way. All right, now, if it's extensive, let's say that I was interested in writing this reaction in terms of, moles of water formed. Instead of moles of 2, we write it in terms of 1. So we divide all the coefficients by 2, half a mole of methane, 1 mole of oxygen, half a mole of CO2, 1 mole of water. And so if you're going to divide the coefficients by 2 in the balanced equation, then you're going to divide the heats as well. So half of the quantity because it's extensive. Also, you can take the first reaction and reverse it. So you have CO2 plus 2 waters down here, forming methane plus 2 O2. And what happens here, there's still 890 kilojoules, but you have negative here, heat's given off. If you reverse the reaction, it's going to be positive because heat's absorbed by the CO2 and water to go back to form methane and oxygen. All right, so there's that. That's one property of enthalpy. Another property of enthalpy is that it is a state function. And the state function, in this case, we're looking at climbing a mountain. And altitude turns out to be a state function, so it doesn't really matter if you change your altitude by doing these switchback trails as you're climbing the mountain to get to the top, compared to going straight up. If you're in great shape, you might be able to do that. And even though the miles are different, the change in the altitude is the same. So altitude has that property that the change in the altitude does not depend on the path. It doesn't depend on how it was carried out. And chemical reactions are the same. All right, so Hess's law involves, or is due to, I suppose, the fact that enthalpy is a state function. And so Hess realized this, and his law, the net value of delta H for the overall reaction is the sum of all the enthalpy changes that take place along a particular path. Another way of saying this is that the magnitude of delta H for a chemical reaction does not depend on the path for the formation of products. And I'll show you what I mean here. So let's say I wanted to go from liquid water to gas phase water. So I wanted to heat it. I wanted to convert it by heating. And for some reason, I don't have a way to get that directly. So let's just say my thermometer is broken, okay? So I can calculate it, though, given information in tables for these different processes. So in other words, instead of going directly, which is what this is right here, instead of going directly from liquid water to gas phase water and, looking the number up in a table even, there's another way to do it. So there's more than one way to get to the answer. So here we go from liquid water to just break it up. So it goes, if you have the ability to do that, maybe electrochemically you could hydrolyze water. The energy needed for that would be to break it up into hydrogen and oxygen. So 1 mole of H2, half a mole of O2, and also it's in the gas phase. Then if you've gone ahead and done that experiment and measured the heat somehow, now you can take this hydrogen and oxygen and combine them to make gas phase water, because they're already in the gas phase anyway. So heat's given off during that process, heat is absorbed in this process. And so Hess's law is saying, and this arrow going down is the same as this arrow right here. So Hess's law says that the sum of the heats associated with this process will be equal to the sum of the heats associated with this process. The other way to say it is this heat minus that heat is 0. So it just depends on how you want to state that. So let's see what I got on the next slide. Okay, so we've written the reactions out. We got water forming hydrogen and half a mole of oxygen. That turns out to be 286 positive. Then the hydrogen and the oxygen form gas phase water. Heat's given off. And so we're going to find this to be true many, many times. When you're adding reactions together, you can cancel the ones that are the same. You got hydrogen and oxygen on the right in the first reaction, hydrogen and oxygen on the left in the second reaction, and then add them up and you get the overall, which is the liquid here going to form gas phase water. And if you're adding the reactions, you're going to add the enthalpies as well. So this is an indirect method to get the heat of that vaporization, and nothing wrong with that. If you measured it directly, you'd get the same result. We figured out the heat associated with this reaction. We might want to tabulate that and say, okay, the heat for the vaporization is 44, right? And all right, I'm going to trim this down a little bit. This is kind of a complicated section, and we really don't need all of it. And I'm being nice because of our situation. So we have, we've got to, let's see, there's different heats that are tabulated. You can go to, Google, but in the olden days, we had all these big manuals you had to go to and look up heats of formation for a compound, or heat of vaporization, heat of combustion, all different types of heats. And Heat of formation is an important one because it's the heat given off when a compound is formed from elements in their elemental form. So, for example, if we're interested in CO2 down here, the elements in their elemental form, so you take carbon, that's going to be the elemental form of it is graphite. Oxygen, the elemental form of it is O2. And you look at the combination of the elements in their elemental form to make the compound of interest and what's the heat associated with that. We're using the rule here that if the elements are in their elemental form, in other words, what form are you going to find these elements in at room temperature, 298 Kelvin, and atmospheric pressure, 1 atmosphere. So with oxygen, it's diatomic. For hydrogen, it's diatomic. Chlorine, diatomic. Magnesium, just monatomic. It just exists as an array, in the solid. It's just each atom is an individual particle. Lead's the same. All the elements are the same for the metals. And then sulfur turns out to be in a ring of 8 sulfur atoms. That's the elemental form. That's the yellow form of sulfur. See lots of photographs of yellow sulfur. If you could Google that, you'd see that. Phosphorus is P4. That's kind of a tetrahedral shape. And then carbon is graphite. That one actually the carbon atoms kind of arrange themselves. They look like hexagons in like a chicken wire. I don't know, you know what I mean by that, but it's got a shape like this. And each one of the points here is carbon. And then also that layer of carbon is connected to the next layer of carbon. And anyway, you can Google that. It looks kind of cool to think about that. So the rule that we're interested in here for the elements in their elemental form is that the heat of formation is 0. Okay, let us just skip the rest of this. So what I'm saying here, don't worry about this stuff right here. And same thing here. We're going to use this first equation, but we're not going to worry about this right here. So in general, if you have a reaction, the heat associated reaction is going to be the sum. The symbol here, the Greek letter sigma, is sum of the heats of formation of all the products. And you get those numbers from a table. And then multiplied times the coefficient for each one. And then you're subtracting the sum of the heats of formation of the reactants. And each one gets multiplied times the coefficient as well. So hopefully I can see without losing any sense of things. Yeah, I can. All right, so, this is a typical table for heats of formation. You can talk about heats of formation of molecules, of compounds, or you could look at heats of formation for the elements in their elemental form. So kind of a summary of what was on the last couple of slides. Let's say I put oxygen in there. The formula would be O2 and the heat of formation would be 0. If I put hydrogen in there, the elemental form is H2 and it would be 0. So you could add all the elements in here in their elemental forms and they would be 0. Okay, so you can pull the heats from this table. And basically, you're going to use the equation. The heat of the reaction is going to be the sum of the heats of formation for the products minus the sum of the heats of formation. Whoops, I wanted to write that out. Never mind. I want to use a symbol. Sum of delta HF for the reactants. And we got to remember to put the coefficients in as needed. Okay, so we're going to do that. I think then here and look at the table. So we're going to pull propane out. Okay, so propane's in the gas phase. And then water, it comes off as a gas, but then when it gets to room temperature, it's going to be the liquid. So I need to write that separately somewhere. Let me write it down. So you got propane, and that is negative 103.85. Oxygen is going to be 0. CO2 in the gas phase, carbon dioxide is negative 393.5. And let's go ahead and use water in the liquid phase, negative 285.8. Okay, now we go. Slide, yeah. What is the heat of the reaction for the combustion of propane? So propane is an organic molecule. Propane has 3 carbons. Prop is the prefix there. That tells you that it's got 3 carbons. ANE tells you got all single bonds in the molecule. If that's the case, then we're going to double the number of carbons and add 2, so it's going to be 8. Don't worry about any of that. 1, 2, 3. 1, 2, 3. Each carbon wants 4. So if you count the hydrogens here, you have 8. Okay, don't worry about any of that. That'll come up later in the course. So we're looking at the combustion here. That means it's reacting with oxygen to form CO2 and water. So what you want to think about then is that you got propane. This propane, I believe, is liquid. It could be gas. Whatever it is in the table, we're going to use liquid propane. I can't remember anyway. Okay, then oxygen gas forms CO2 gas, and then we're going to do, let me look at my notes here. Okay, I actually don't think I have my notes on that one, so let me back. I wrote it all down. So I don't know what, I think I said it was in the gas phase, right, for the propane. And then we're going to use water in the liquid phase. Okay, so if we want the heat of this reaction, if we want to calculate it, we go to the table. So I'm just showing you how to use the tables here. Delta H, nope, that's wrong. This is delta H for the combustion, but we'll just go ahead and say reaction, same thing. So this is going to be the heat of formation of CO2 plus the heat of formation of water. Wait a minute, I didn't balance it, hold on. Okay, we got 3 carbons, we have 8 hydrogens, and then the oxygens is 4 and 6 is 10, so that's going to be 5. Okay. So it's going to be 3 times the heat of CO2 plus 4 times the heat of formation of water. That is the products here. Then we're going to subtract the heat of formation of the reactants. So you have 1 times the heat of formation of propane, C3H8, and then you're subtracting the sum of these two, 5 times the heat of formation of O2. And that would be in red there. So those are the coefficients. Okay, and then this would be for the reactants. So it's always products minus reactants. Now I take the numbers, delta H for the reaction is going to be 3 times the heat of formation of CO2, negative 393.5, plus 4 times the heat of formation of water, negative 285.8. Then you're going to subtract 1 times the heat of formation of propane, which from the table is negative 103.85, and then it'll be 5 times the heat of formation of O2, which by definition there is 0 because it's an element in its elemental form. All right, let me calculate this. Oh dear, I'm losing my notes. 3 times 393.5 is, see if that makes sense, negative 1,180. And then the next one will be negative, so 285.6 times 4. 1142. I'm not worried about sig fig here, sig figs. And then minus a minus, so it's plus 103.85, or we just call that 104, I guess. And then we have 1180 plus 142, and then subtract 103. So this is going to be negative 2218. Let me double check on that. 1180. Okay. Well, I might have made a mistake, but I did get the same answer twice. So heat of the reaction, and these are kilojoules per mole of propane consumed. This is very, very common to calculate the heat of a reaction, so it's very, very important that you know how to do this right here. All right, now the next slide gets a little bit complicated, but this stuff's actually kind of fun. Back in the old days when I made these slides, I was using just typing lowercase l. It looks like an I in there, but L is for liquid here. And it's everywhere. Okay, now we're going to use Hess's law, which says, okay, we don't know how to go directly, we don't know how to calculate the heat directly for this formic acid molecule decomposing to form water and carbon monoxide. Well, let's say we don't have it, but we can calculate it given this information right here. And everything I told you about Hess's law we're going to use here. We could flip the reaction, you know, we could write it the other way, and then that would just change the sign here. If we needed 3 of those, then we're going to need 3 of these as well because they're proportional, things like that. So how to approach this problem is the issue here. And you want to rearrange the given reactions so that they, a couple of steps here. The first step is just to get everything kind of lined up the right way. This is the way I do it. Everybody has their own way of doing it. I'll do it my way and then comment on why it's the better method. So if I have formic acid on the left here, I need to flip this reaction and have the formic acid on the left there. If I've got carbon monoxide on the right in the reaction, I got to have it on the right here, so I'm going to stay on this one. This one's not so clear what to do with water because lots of times it ends up on both sides of the reaction. But because it's on the right here, let's go ahead and keep that one on the right. So what I'm saying here is that I'm going to flip the first one, stay on the second one, and stay on the third one. So I will say formic, I leave off the phases on this one too. You don't need the phases. Although the heats are associated with the phases. If you're looking up the numbers in the table, you need to know what the phases are. So if I'm going to flip the equation, I'm going to take the negative of what's in the parentheses. I'm going to stay on the hydrogen and 1/2 O2. Forming H2O, and therefore I'll have just 286 here, negative. And I'm going to stay on the last one, carbon plus 1/2 oxygen form CO. And that one stays, so it'll be 110 like that. Okay, now for this one, I don't think we have to multiply times any coefficients. This is kind of a simple example, just so you get a sense of things here. And if I added them up, what would happen? So I've got hydrogen cancels. We get half oxygen plus half oxygen is 1 oxygen, which cancels with the oxygen on the right. And then the carbon cancels, that's graphite. And so we have HCOOH forming H2O plus CO. This is exactly what is in the box, and that is the goal here, to get things arranged correctly. So this is going to be positive 409 minus 286 minus 110, and delta H, let me find that here, 13.0. So delta H for the reaction is 13.0 kilojoules per mole. All right, there is another way to do this problem. I'm just going to point it out quickly here. So we'll say method 2. And method 2, since these are all, they happen to be heats of formation, we can just take the heat of formation of the products minus the reactants and get the exact same answer. This is just a coincidence. When you're given equations that you're going to work with, they're not always heats of formation, but in this case they are. So we would say heat of the reaction is the sum of the heats for the products. So that's water and the CO. And this is going to be negative 286 plus a negative 110. So that's products minus reactants, which is just the formic acid. So minus a negative 409. And if you look at what we just did up here, we kind of did that, right? Positive 409, negative 286, negative 110. So it's easy to use either method here, but in general it's not. So just kind of ignore this method too. All right, one more slide to go. This is going to be hard for delta H. Whoops, difficult one. And I'm going to take a quick break. All right, last slide then is the most difficult example for the chapter. And you have C2H2, that is acetylene, reacting with 2 hydrogen molecules to form ethane, C2H6. So you are given some information, and you have, in this case, a combustion reaction of C2H2 to form CO2 and water, the heat associated with the combustion. Similarly for the C2H6, that's a combustion reaction. And then this last one is a heat of formation of water from the element in the elemental form, 286. All right, and then we're going to use the same technique where we line things up first. That's kind of my strategy here. So let's think about that. Now, since you have C2H2 on the left, we're going to keep it on the left in this first reaction. Then you have C2H6 on the right-hand side. So the second one, we're going to flip and put the C2H6 on the right-hand side. And then you have hydrogen on the left-hand side, and we're going to keep this reaction the same. So I would make a note of what I'm doing so I don't forget. I would say we're going to stay on the first reaction. We're going to flip the second reaction and stay on the third reaction. That is a good thing to start with, just mapping out your strategy. Don't worry about multiplying times anything. All you want to do in this next step is just get everything in the right place. So the first one is going to stay C2H2 2 of those, plus 5 O2s, forms 4 CO2s plus 2 H2O, and that's negative 26 O2. Second one we're going to flip, so just take the coefficients and everything. 4 CO2 plus 6 H2O forms 2 C2H6 plus 7 O2. And that is the negative of what's in the table, negative 3123 in the table. Take the negative of that. Just making a note of it now. We'll actually make that positive in the next step. Okay, and then we're going to leave the hydrogen the same. So H2 plus 1/2 O2 forms H2O, and we have negative 286 for that one. Okay, and we're trying to get what's in the box here. So your coefficients have to be proportional. All right, now you got to follow me on this. There's 1 as the coefficient in the reaction. We have 2. You could multiply this first 1 times 1/2. Some people teach to do it that way. I strongly discourage that because you're going to end up with all these fractions in here. And you're adding fractions and multiplying coefficients times the fractions, and it just gets very messy. So it's better to keep it as 2. Notice you got 2 here. So 1 to 1, and we've got 2 and 2. Let's get all the way through it, and then we'll divide by 2 in the end, okay? So here's the strategy. If we added these together, we would have 2 C2H2s and 2 C2H6s. So to keep the proportions the same, 1 to 2 to 1, the question is what coefficient do we need right here for the hydrogen? Since this is double and that's double, we're going to double this hydrogen as well. And so we are going to multiply this equation times 4, and then the number of the heat will be times 4 as well, times 4. Okay, so I prefer to rewrite it over and over and over. So what I'm talking about is C2, 2 of those, plus 5 O2s, 4 CO2s, 2 H2O, negative 26 O2. Then the second one, 4 CO2s plus 6 H2O, forms 2 C2H6 plus 7 O2s, and that's positive 3123. And then you have 4 H2 plus 2 O2s forms 4 H2O, and that'll be 4 times 286, hold on, 286 times 4, 1144, that is negative, let me double check that, 286 times 4. All right, so now let's see what we got here. First of all, let me repeat what we just did. We have double what we need for C2H2. We have double what we need for C2H6. We have double what we need for H2 in this reaction. So 2 to 4 to 2 is the same, or can be divided by 2, and you'd have 1 to 2 to 1. I always get a lot of questions on that. All right, so we are going to cancel what we can. The CO2s are going to cancel. We have 2 plus 4 waters. They will cancel with 6 waters right there. Then what else can we do? A different color here. We have 5 O2s and 2 O2s. They can cancel with 7 O2s. So we have 7 on both sides. And then added up, we got 2 C2H6 plus 4 H2 forms 2 C2H6 The sum of that is negative 623. And we're not finished yet. We have to divide everything by 2 in order to match what's in the box. So divide by 2. And then we have to divide this by 2 as well. So negative 623 divided by 2, negative 311.5, or we could say negative 312 kilojoules per mole of anything with a coefficient of 1. That is going to be delta H for the reaction. Difficult problem indeed. There is a problem on your group activity with the same level of difficulty, so you can practice it. Look in your textbook at the problems at the end. You'll probably find a couple of them there as well. So I hope you take this challenge and figure out how to do this problem. It's a good one. That is my stomach growling. All right, have a good day. Talk to you later.